In this short video I plan to prove to you the equation that you're going to use for the time period of a pendulum. There's a few assumptions we make in this which you need to be aware of, so I'll point those out when we get to them. So we'll call the length of the pendulum L, the mass of the bob on the end of the pendulum M, which means the weight of the pendulum is mg, and we'll call this angle from the vertical theta. So these two arrows, the red arrows, are the components of the weight acting parallel to the string and perpendicular to the string. So because the weight is vertical and this line is vertical, then this angle here is also theta, which means that this component is mg cos theta, and this component is mg sine theta. And we're going to call this displacement from the equilibrium x. What we're trying to do is get an equation in the form A is equal to minus omega squared x, because that's what we understand to be the basic form for simple harmonic motion. So we know the acceleration of this object according to F equals ma is the force over the mass, and the accelerating force is going to be this one, mg sine theta. So we have mg sine theta over m, and we need to work out what sine theta is. Now if theta is small, typically less than 10 degrees is the recommended angle that you keep it under, then sine theta is equal to, or approximately equal to, tan theta, which, if theta is small, then x will be small, and we can approximate this to a right angle triangle. Then tan theta is x over L, opposite over adjacent. So providing we do keep this angle small, you can prove it for yourself that tan theta equals sine theta for small angles, close enough anyway. Then providing this angle is small, then sine theta is x over L. So substituting that into here, the acceleration of the object is, well, the m's cancel, g x over L, but the acceleration is to the right and the displacement is to the left, so we end up with a negative sign. Now we've got something which is in this form: a equals some constant times x, or minus x. So from that we can see that g over L is equal to omega squared. So omega squared is equal to g over L, which means omega is the square root of g over L, but it's also equal to 2 pi over t. So rearranging that, we get the time period of a pendulum is equal to 2 pi square root of the length over g. Now notice that there's no mention of mass in there, so varying the mass of the bob according to this theory has no effect. However, what I have done is I've assumed that the string has no mass, and this force is acting from the centre of mass of the bob. So in reality, changing the length of the pendulum does shift the centre of mass slightly because the string has a mass. Okay, now you can minimise that effect to become somewhere close to this if you have a very, very thin string and a very large mass. But bear in mind that it is an approximation, a good approximation, but it is an approximation.